Well. What have we got here? This is one of these problems that are similar to 1053. I'm going to try the xenon trifluoride. I think this is from 1054. Oh, I'm sorry, xenon tetrafluoride. There it goes, xenon tetrafluoride. So, of course, xenon, there's only one of them in the formula, so I put that in the middle, the c.b.a, the central bonding atom. And I'll just surround it with these fluorides here. How about that? Surround it with these fluorides, just the way Sam did in class. Surround it with the fluorides. Why am I surrounded? Because it's the central bonding atom. Silly. Alright. Now I'm going to make a little bonds because, of course, this is chemistry. There are bonds, right? 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 Not James Bond, sillies. Oh, right. It's covalent bonds. Covalent bonds.
Ionic bonds too?
That's covalent bonds.
Oh.
Okay. So here's the xenon. Oh, let me make this a little smaller. Not that Xena, it's xenon. Oh, okay. So I'm gonna draw the xenon here. Xenon has 8 valence electrons because it's in that last group on the periodic table. Fluoride.
What is it, Valencia?
Fluoride. Not Valencia. Valence electrons.
Oh.
Wait, fluorine has 7 valence electrons, and then there are 4 of them, so that's 28. So the total is 28 plus 8, which is 6 electrons. Alright. So now I'm going to give everybody an octet using this spray paint type tool. So everybody gets an octet. So I'm going to just add all the lone pairs. Right now, like Sam says, I'm playing God. So I'm putting the electrons where I think I want them to be. The reason why I'm picking these positions is because I want everybody to have at least 8 electrons around them. Xenon in the middle there already has 8 because it has 4 bonds, and each bond is 2 electrons, right? So now these fluorides, they all have 2 electrons from the bond there, and I want them to have 8, so I just add 6 more, 3 pairs. And now I'm going to count these electrons here. So let me use the pencil tool to count. Can I get a different color? Can I just get green? Thanks. So here's I'm counting. This is 2, 4, 6, and here's 8, and then 10, 12, 14, 16, 18, 20, 22, 24, and then there's 2 in here. This is 26. 28, 30, 32. Oh, 32 electrons, but I need 36. So, of course, just like Sam did in class, gotta give somebody an expanded octet. And who's eligible? Well, this person is eligible. Right here. This person is eligible. Why is this person eligible? More on that later in a different file. How about that? Alright, so now I have 36 electrons total. I had 32, and this is 34, and that's 36. Great! That's the Lewis structure. Oh, thank you very much. Oh, wait. Okay, so if that's a Lewis structure, that's not the answer. The answer to the problem is what is a hybridization. So, how many electron groups are around this xenon? How many electron groups? Let's count them. Let's see. I'm going to use green again. That's 1 electron group. That's another electron group. That's 2. That's 3. That's 4. That's 5. That's 6. 6 electron groups on the xenon. 6 electron group. Oh, sorry. Do you remember Sesame Street, the count? You might be too young for Sesame Street. I like Sesame Street. Alright, so now, here it is. Xenon had 6 electron groups, and remember from the table that we drew yesterday, Sam drew yesterday, 6 electron groups. That means the hybridization is sp3d2. You want to prove it? Let's count them. There's 2 here. There's the 2. Whoop. Plus 3 is 5, and the invisible 1 is here. 5 plus 1, that's 6. That's right. 6 electron groups. The hybridization is sp3d2. And now this is problem 1054C. And then this problem does not include the geometry and the shape of the electronic geometry, what's that other called? The molecular geometry, but let's do that just for kicks. So with these lone pairs, there are 6 things hanging off of this xenon. So you look in that table that's sent on the board on Sunday, and you see that this is going to be octahedral geometry for the electronic geometry. But for the molecular geometry, well, the biggest things that are hanging off of this xenon are the lone pairs. So the lone pairs get the top and bottom position. So let's see if I can draw it purple. So the biggest things, I'm going to draw it over here. The biggest things that are hanging off of the xenon are the lone pairs, right? So those get the top and bottom positions because those top and bottom positions have the most elbow room. And then the fluorides will just take positions over here. So this electronically, of course, is octahedral, but if you just look at the atoms, this is square planar. Square planar. The angle between these fluorides is 90 degrees, but notice that the angle between anybody and the lone pair, these lone pairs, is 180 degrees. Because this is a plane. That is a plane. And so the angle between the lone pair, and this lone pair has like 180 degrees of elbow room. This lone pair has a full, this lone pair up here too, blue. This lone pair has a, whoa, what happened there? Okay, click okay. This lone pair, woo! This guy up here, I'm talking about this guy up here. This lone pair has a full 180 degrees of room to, oh, I'm sorry, I'm messing up. 180 degrees of room to play. Square planar for the molecular geometry. Bye.